In this video, we'll discuss what strong bases and strong acids are. The common acids and common bases are something we should remember. If you just look at common acids, hydrochloric acid, which is a very strong acid, sulfuric acid, phosphoric acid, these are generally called mineral acids. They are inorganic acids. They are not organic acids, and they are mostly very strong acids. Here you see acetic acid, and the most acidic proton is this proton right there with pKa value of 4.8. So most of the organic acids, since they are weak, their ionization constant, or Ka, can be measured, and it's very low ionization constant, and therefore they have pKa value associated with them. So the pKa value for organic acids, as we have already discussed, it ranges from low 3.5 to maybe pKa of 50 in our previous discussion. So acetic acid is a weak acid. It's a weak organic acid. Here you see another strong acid. Actually, even though it's an organic base, it is a sulfonic acid, pKa of -7, which is comparable to the hydrochloric acid. So common acids, usually they deliver proton in aqueous solution. That's what you see here. So the ionization is very high, therefore they have high Ka constant or very low pKa values. So if you just look at some bases, common bases, if you just look at sodium hydroxide, which is a very strong base, this is a strong base, sodium amide. So you should remember that the basicity comes from the negative charge they carry or the electrons that are available to abstract a proton. So these are the spectator ions, the sodiums, that are not part of the basicity of the compound. The basicity comes from the hydroxide, which is the ionized hydroxide ion, which is a negatively charged ion. So mostly what you need to remember would be bases have always carry a negative charge, or they have a pair of electrons, or they have a pi electron that is available to abstract a proton. So protons are positively charged. If you just look at here, the ionization of this acid gives always H plus and Cl minus. So here the conjugate acid is H plus. Here, if you just look at sulfuric acid, it gives off two protons that are positive. So the acids, most of the acids carry protons, while most of the bases carry either a negatively charged species or a pair of electrons. So here, these are the spectator ions, which are not part of the basicity, but the basicity comes from hydroxide ion, amide ion. Here, if you just look at here, hydrogen, here it's carrying two of the electrons, and it's called hydride. So sodium hydride is a very strong base. Sodium hydride. This is sodium hydroxide. This is sodium hydride. So the hydride ion, which is a negatively charged hydrogen, don't confuse it with a proton, which is H plus, which doesn't have any electron on it, but a positive charge. This is an acid. But here, the hydride with two electrons on it carries a net negative charge, and hence it is a very strong base. Here, if you just look at here, it is a base that is carried on oxygen, that is a negative charge is on oxygen. This is called sodium acetate, sodium etoxide, and the etoxide ion, anion, has a negative charge on it. So the oxygen is carrying the negative charge, which makes it a very strong base. Here, if you just look at here, tertiary butyl oxide, which is an etoxide type, which has the oxygen, which is carrying the negative charge, still is a base. So you have to remember that here a nitrogen base, this is diisopropyl and lithium, but the negative charge is on nitrogen. That makes it a very strong nitrogen-based base. Here the basicity comes from the lone pair of electrons on nitrogen. These nitrogens are available to abstract a proton. Therefore, the basicity of this compound, this is triethylamine. A triethylamine is a base because of these two electrons. Here you see another compound with nitrogen. So nitrogen carrying a lone pair of electrons. Those pair of electrons are available to abstract a proton. Therefore, this compound, actually called pyridine, is a base. So because of this pair of electrons on nitrogen, that compound is a base. So the most characteristics of a base is either a negative charge or a pi electron system where you have abundant electron density on them. So this is ethoxide, this is tertiary butyl oxide, this is N-lithium, called, this is a counter ion, just like sodium. This is a positive ion, but mostly the nitrogen is carrying a full negative charge on it. Here nitrogen has a lone pair of electrons, so the basicity comes from this lone pair of electrons. Here, as you see, pyridine has a lone pair of electrons on nitrogen. That makes it a base. So clearly there is a big difference between the acids and the bases. The acids always, they produce a proton or they donate a proton. Here they have mostly electron on them. So negatively charged species or a pair of electrons makes a compound a base. So you should practice this and understand what are common bases and what are the common acids. Now, by expanding our definition for acid and bases, there are definitions of an acid, loose acid, for example, and loose bases. So these are examples of loose bases. These are examples of loose acids. So in general, a loose acid is defined as a substance that is electron deficient or it has a positive charge on it. Let's see each one of them. Boron trifluoride, as you know, if you were to draw the loose structure, it doesn't have the octet satisfied, which has 6 electrons around it. It means it has an empty orbital that can take up electrons. Therefore, since it can take up electron, it is defined as a loose acid. It has an empty orbital where it can take a pair of electrons here for boron. Aluminum chloride, the same. Aluminum chloride as a central atom, if you have this, octet is not satisfied. There are only 6 electrons, as you see. Therefore, it acts as a loose acid. It can take extra pair of electrons. Here, as I said, this is an organic cation, a positive ion. This is tertiary butyl cation. As you see, the carbon is electron deficient. Electron deficient, hence it has a formal charge of positive. So anything that contain an electron deficient center or a positive charge would also act as a loose acid, because this can be attacked by a loose base if electrons are transferred to this. So basically, a loose acid in general, you should remember that it has either an empty unsatisfied orbital or a positive charge that can be neutralized by a negative charge or electrons. In the definition of loose bases, they are not contradictory with Bronsted-Lowry definition of acid base. A base always contains electrons that can be donated to a loose acid. Here, for example, a hydroxide ion, has an extra pair of electrons that can be donated to a loose acid. Here, ethanol with oxygen containing those lone pairs can act as a loose base, because based on what it's interacting with, those pair of electrons can react with any loose acid or any acid compound. Here, the acidity of this compound, as you see, this is a very neutral molecule, 18, but we can consider this based on what it is interacting with as a base, as a loose base. And the reason becomes that pi electron is movable or can be donated or can interact with a loose acid. So extra pair of electrons. So the definition of acids and bases now is becoming more expanded and almost covers all compounds, because you can use the Bronsted-Lowry definition for acids and bases, and now you can also apply the loose acid and base definition for any compound. So for this compound, if you were to ask, this compound would satisfy being a loose base because of those pi electrons. The pi electrons on this makes it a base. Here, Br minus, the bromine anion, as with a negative charge, as long as the electrons can be donated, bromine minus acts as a loose base. So anything that contains a negative charge due to extra electron pair would satisfy as a loose base. Here is water. If you remember water, it can act both as a loose base or also a Bronsted-Lowry acid. So if you just look at this pair of electrons, those are extra pair of electrons, just like what you see on ethanol. Those electrons can be interacting with any loose acid, and hence the water becomes a loose base. But based on also what it is interacting with, this proton also can be also acting as an acid. So it's always a matter of relative strengths of acidity and basicity. So those protons, if they were pulled, in that case, water was acting as as an acid. So based on what it's interacting, what counterpart in the reaction is, a compound can be a loose acid or a loose base. Here in this case, because of the lone pair of electrons, water is acting or could act as a loose base. Here I'm just showing a reaction that shows that a pi electron system like this one, a pi electron, having a pi electron makes it a loose base, right? Based on the definition we have, this compound, cyclohexene, organic molecule, by just looking at it, if somebody asks you whether that's an acid or a base, you don't see any protons that are attached to oxygen or anything like that. It could be confusing, but based on our definition now, since it has a pi electron system on it, this acts as a loose base. Obviously, hydrochloric acid is an acid, so this pair of electrons can just take out that proton. Then now you are adding one more hydrogen, which is this hydrogen, for example, is added. And when this pair of electrons is taking that proton, it leaves a positive charge, obviously, on this, and Cl- is the conjugate base. So in the pi electron, having those pi electrons taking up that hydrogen, this makes it a loose base, and this is the acid counterpart. And now here you have a conjugate acid, and here it is a conjugate base is created. So in in expanding your definition of acidity or basicity of a compound, you can apply both the Bronsted-Lowry acid-base definition or also a loose acid-base definition. So almost all organic compounds or any compound, you can classify it as an acid or a base based on also what it is interacting with. So in the next discussion, we'll see some reactions of loose acids and loose bases. To further help you with understanding of loose base and loose acid definitions, I have this 4 problems for you to identify which one is a loose acid, which one would be a loose base, and give the products of possible products of the reaction. So applying our definition for loose acid, loose base, the Cl- with its pair of electrons on it, Cl-, is a negatively charged species, and it has abundant number of electrons that can interact. Therefore, by the definition, Cl-, the chloride anion, is a loose base. We call this loose base. And it's interacting with boron trichloride. Boron in the periodic table, if you just look at that, usually it doesn't have a satisfied octet when you have products like BCl3, boron trifluoride. All those are loose acids because of the empty orbital that boron can accommodate more electrons, because it has to satisfy an octet rule to be 8 electrons around boron, but naturally it exists as a electron deficient species. It makes it a very reactive compound, and it acts always as a loose acid because of the electron deficiency. So we call this loose acid. So the interaction between Cl-, which is chloride anion, which is a loose base, and boron trichloride is a loose acid-base interaction. Okay. Now we have also this compound in B. You have ethylene. It has a carbon-carbon double bond. Remember what we have discussed before. If you have electron density that can move or act or interact with other species, that is considered as a loose base. So remember, expanding our definition, here in this reaction, this compound is acting as a loose base because it has extra pair of electrons on carbon-carbon double bond. So the basicity just comes from the pi electron system. So anything that contains a pi electron system can act as a loose base. Here, sulfuric acid, obviously sulfuric acid is a mineral acid, a very strong acid. You know that, therefore this is a loose acid. Okay, in reaction C, what you see here is boron trifluoride. Like what I gave you an example, all borons here, because boron is electron deficient, usually it acts as a loose acid. So this is a loose acid. And as I said here, the oxygen is containing always a lone pair of electrons. So the basicity comes from those lone pair of electrons on oxygen. Therefore, ethanol in this case is acting as a loose base. And this is a loose acid. How about in the reaction shown in D? If you just look at this species and somebody gave you to identify which one is a loose acid and a loose base, you look for a cation here. A cation means electron deficient carbon. That carbon right there has lost electrons, so it doesn't have electrons. It's a positively charged species. Obviously, that is the loose acid. So this is a loose acid because of the lost electrons. This is a loose acid because of the positive charge. So now expanding your understanding of what an acid and a base tells you that almost all compounds can be classified as an acid or a base based on what they have. So loose base is this one, obviously would be a loose base because of electron pairs, lone pairs on water. Now water is acting as a loose base. So remember to review all this, and all of the definitions for loose acid, loose base can be summarized by this exercise here. Therefore, now let's do what the products look like. Here, a loose acid interacting with a loose base, the product would look like the pair of electrons would attack the boron, which is electron deficient, and it would create something like this. And a negative charge on this. So you are creating that species. This is a tetrachloroborate kind of species. Here, what would be the product if you just take those pair of electrons and move away one of the protons from the sulfuric acid? The product looks like you have CH3, C, one of the pi electron system has gone out, therefore you have CH3, but one hydrogen is added here, and since one of the hydrogen is transferred, that is the product you see. So a plus charge because the pi electron has been moved out from carbon. You left a plus, but you are adding one more proton, that is the acid. So this is a species. So remember that we have a neutral system. Here also a plus-minus system, so charge is conserved as well. So make sure that your reaction products are consistent with what you have done in the reaction scheme. Here a loose acid, loose base interaction would give you boron, fluorine. Fluorine is obviously like that, but since oxygen has come from this with a pair of electrons, the electrons are donated to boron, so that's minus, that is CH2, CH3. So a plus and minus is created, but this is the interaction. Here in this case, this electron would attack that carbon. So remember the direction. Here the direction is like that. So the pair of electron attack the boron center. Here the pair of electron picked up a proton from sulfuric acid. Here the carbocation, or the positive charge on carbon, was attacked or satisfied with a pair of electrons on this. Now the product looks like so. That is now a positive charged reactant also gives you a positively charged product. So charge is conserved. So this is a loose acid, loose base interaction giving all those products. So remember now how to identify a loose acid or a loose base in a reaction, like what we have done. Chloride minus is a loose base. Boron trichloride is a loose acid. So we have all this according to the definition for loose acids and loose bases. And remember also how to write the products that are results of a loose acid, loose base interaction.